All right, welcome to the quantitative or math-based part of our mole-to-mole ratio discussion. Mr. Gamboa posted kind of a discussion about bikes and frames and chemical equations and how they're kind of similar and how ratios are kind of similar in how we make bikes and also how we produce chemicals as well. So let's look at a couple of chemical reactions and we'll do a couple problems that will be similar to the WebAssign that is assigned to you. So let's look at number 2 on this worksheet that I found. Basically, we're going to try to do letters A and B here. Let's look at letter A first. So it says 20 moles of NH3 are needed to produce blank moles of H2O. It's basically what we're asking. It's kind of like the bike question from before. If we had 20 wheels, how many bikes could we make? The NH3 is a reactant, so it's one of the ingredients, kind of like the wheels were, and H2O is a product, so it's one of the things that we end up with. So in order to solve this problem, we're going to need to balance it. We're going to need to figure out what the ratio is between the different compounds that are in this reaction. So we did balancing last unit. I'm just going to set up a little table here where we balance the amount of nitrogen, hydrogen, and oxygen on each side. I'm going to guess here that we put a 2 here. I'm going to try to fix the nitrogen first. So I'll have 2 nitrogens on each side. Currently I have 6 hydrogens over here on the reactant side. So maybe I'll put a 3 right here. So that way I'll have 6 hydrogens on the other side. Lastly, my oxygens, looks like my oxygens are off right now. I have 3 on one side and 2 on the other. You know what? I think I'm going to take a step back and try to balance this one out, and maybe I'll have you guys do the same thing. Because currently I have 2 oxygens on one side and 3 on the other. It's kind of end up like this. So the video is going to pause now, and I'm going to ask you to try to balance this out since we're not quite finished yet. Our oxygens are out of whack. Whew. All right, that took me a little bit of time. That was kind of a tough balancing problem. We have our coefficients are 4, 3, 2, and 6. So sometimes doing these problems, the balancing takes a little bit more time than the actual problems do. But at any rate, it looks like we have a ratio here of 4 to 3 to 2 to 6. So this is the ratio of how many of each compound we can make. So let's go ahead and use these ratios in order to solve letter A. So we have 20 moles of NH3, and we want to figure out how many moles of NH3 we need to produce blank moles of H2O. So basically what we're asking is how much water can we make? How many moles of water can we make with 20 moles of NH3? So let's start our problem. We're going to actually use the bridge method for this problem. So we'll start by writing what we're given. That's the first step of the bridge method. 20 moles of NH3. The next step of the bridge method, write a fraction bar. Mr. Gamboa likes to kind of do boxes, but this is my way of doing it. And your units. So we want to get rid of moles of NH3, and we want to end up with this unit, moles of H2O. The next step is to make the top and the bottom equal. Now, what numbers can we use to make the top and the bottom equal? Well, since we understand how ratios work from Mr. Gamboa's awesome video, we know that the ratios in a chemical equation help us to balance it so there's the same amount of mass on each side. The mass before is going to be equal to the mass after. So since that's the case, we can use these numbers, these ratio numbers, these coefficients in our bridge method, in our unit, in our conversion right here. So we know that for every 4 moles of NH3, we can produce 6 moles of water. It's kind of like when we were saying for every 2 wheels we can make 1 bike. Well, for every 4 moles of NH3, we can produce 6 moles of water. So once we've done this, we can kind of cross out moles of NH3, and we're left with 20 times 6 times our unit of moles of H2O over 4. 20 times 6 over 4, that answer is 30. So, if we started with 20 moles of NH3, we can make 30 moles of water, of H2O. So in the next problem, we're actually not going to look at water and NH3. We're going to look at other things in the equation. So we're going to look at oxygen and nitrogen. So let's try to do letter B. So we've said that we have, well, it says how many moles of N2 will be produced if 3 moles of oxygen react. So this word react here, think of it like in a bike factory, meaning like used up. So if you use up all of the wheels or all of the frames, it's kind of like in a chemical reaction, the chemicals being used up or made. So we're going to say that 3.5 moles of oxygen have been used or used up. We want to find out how many moles of N2. So we've used 3.5 moles of O2. We want to find out how much N2 we can produce. So we're going to go ahead and set up our units once again so that O2 moles of O2 cancel out, and we end up with moles of N2. Where do we get our numbers? But of course, we get it from the ratios that are right here that we found earlier when we balanced the equation. See, things in chemistry build on one another. Last unit we learned how to balance. This unit we're using that balancing for something useful. So for every 3 moles of oxygen, we can make 2 moles of nitrogen. It's a 2 to 3 ratio. 2 to 3 ratio. 2 to 3 ratio. So what we got to do is get rid of our moles of O2. They're diagonal. They cancel out. And we'll end up with 3.5 times 2 moles of N2 all over 3. If we multiply that all out in our calculator, 2 times 3.5 divided by 3, we end up with 2.3 moles of N2. So basically, it's kind of like that bike factory example, just like it. We have 3.5 moles of O2. If you look at the reaction a little bit closer, we could probably predict that it should be about 2.3 moles. Here's what I'm talking about. So we had 3.5 moles of O2. That's really close to 3. So our ratio is probably really close to 2 here. So the ratio of 3.5 to 2.3 is really close to the ratio of 3 to 2. So since they're close, we can kind of say, yeah, that answer makes sense because these numbers are pretty similar to one another. Well, there you go. Those are 2 examples of how to use mole-to-mole ratios to understand or to predict how much you can produce of a certain chemical. And then whenever you get confused about this, just think back to the bike example. You have products like wheels and frames, and you have, reactants like wheels and frames, and you got products like bikes. It's no different with these chemicals, and the biggest thing is to know that the balanced equation gives us the ratios we need to put into our unit conversions that are right here. Good luck on the web assignment. Let us know if you have any questions on Classroom.